that concrete practical, you know that concrete consists of particles, aggregates, sand, cement, and water. And then we spoke about it in terms of the different types of cements that you can use depending on the strength that you require. And also you need to make sure that the soil or the sand that you're using is clear from certain materials, and why is that important. All of that was discussed during the practical. And remember that also the water that you need to use when mixing or creating concrete, it has to meet different certain standards, so that you don't end up with concrete that is not reaching the required strength that you may need, right? So we're going to move forward and go deeper into the properties of hardening concrete, and also talk about the strength. And we're also going to discuss the different materials in concrete, but most importantly, then we're going to do the concrete mix design calculation. So I will need you to have with you your book, a textbook that you collected on campus, a calculator, a book that you can write on, and yes.
Unfortunately, I do not have a book. I wasn't able to collect one when I was at what's it called thing from last week Thursday.
Yeah, I think Jordan, that will be a personal decision. I don't know how that happened on your side, but yeah. So I don't know what happened, but yeah, that was not supposed to happen. So I
Okay,
don't know how you ended up with no book.
that's fine. Is it possible next time we I meet you when we're doing projects, please collect one?
Yes, you can collect it, but I can't right now. Right now, we're not allowed on campus.
That's
So yeah. So as soon as it opens, you will get your book. Uh, so
Thank you.
please, yes. So I would, because I'm under the impression that okay, you're supposed to have your textbooks with you. I did not really bother into cropping the tables, because when you're doing the mixed design, you need the tables that you're going to refer to, and they're all in your books. When you're writing, they will be attached as annexures, and that's what you will be using. So let's just start and then discuss it, and then on the last hour we will do the mixed design. So like we said the last time, we discussed the properties of hardened concrete. Indicate if you don't see the shared screen, but I've already shared my screen with the slides on them. So I'm under the impression that you can see the screen, right? Remember we said that we have properties of hardened concrete. How does concrete harden? Concrete hardens because of the cement. We said that we have different types of ingredients that we use in concrete. You already know those, right? And we said that this concrete will harden. How it hardens? It will harden because of one ingredient called cement. So cement is the one that works as a binder to mix all these ingredients together. So cement, with the aid of water, will form a paste, and then it has different properties, and then we will discuss that as we move forward as well. Right. So when we spoke about hardened concrete, we said that we really focus on the durability, and we also said that the durability is the ability of hardened concrete to resist the natural elements. Which are those natural elements? We said rain, wind, the sun, and so forth. And we spoke about the compressive strength that is usually considered the most important property of hardened concrete, right? So we also added and said that The reason why we'll have reinforcement on concrete is because concrete is very strong on compression and very weak in tension. Therefore, we'll need reinforcement to make sure that we fix that problem. Now, for you to determine the compressive strength, that is how you determine the compressive strength. The compressive strength is determined by the formula force over area, right? So the compressive strength of concrete equals force over area. This is just one example to maybe kind of we are going to look into in terms of the compressive strength, so that maybe you understand what are we talking about when we say force over area, right? So here what they tell you is, like I said, the idea here is for you to understand that the compressive strength equals force over area. The other thing in terms of information, you will have to think and see if you are able to understand a question or not, right? So let's say here's a question. They say calculate the approximate number of people a 100 millimeter concrete cube can support in compression. Assume the average mass of one person is 70 kilograms and the strength of concrete is 25 newtons per millimeter squared, right? So this is the information that they gave you. They say, calculate the approximate number of people, right? A 100 millimeter concrete cube can support in compression. Why? Because remember, previous slide, we said that we're dealing with the compressive strength, and we said that we understand that concrete is strong in compression, but weak in tension. And then we come back and say, calculate the approximate number of people. They don't say determine the compressive strength. They just tell you that calculate the approximate number of people 100 millimeter cube of concrete can support in compression. When you're assuming the average mass of one person being a 70 kilogram and the strength of concrete is 25 newtons per millimeter squared. So if I may ask, if you were to get a question like this, how would you go about answering the question? Provided you already know that compressive strength equals force over area. Anyone?
Yes, ma'am.
Okay.
Yes. I think when you would use the compressive strength, which is given the 25 Newton per meter squared, and you apply it to the formula. Compressive strength is equal to F over area, and you get the force, and you convert the force to kilograms, and then you divide by the 70, and then you will get a number of I think that's how we do it.
So you're saying that we need to convert the force into kilograms?
No, I was saying that I was going to use the formula compressive strength is equal to force over area to find the force that the concrete. Yeah, I'm not sure if I'm making any sense.
Okay, is there anyone who would like to try? In the meantime, can we try to do it on the sides, like, because you already have a book and a calculator? In the meantime, do we agree with the gentleman that just shared his answer? Yes, no? Or is there anyone, do you agree, or you have a different method that you think we can use? By the way, if I may ask, sir, if you say we're going to use the formula for the compressive strength, which is force over area, which force are we using?
I'm saying, ma'am, you use that formula as a man was saying, that you use that formula to find the force. Is the 25
Okay.
is the 25 Newton per meter squared? Is that not the compressive strength? The compressive stress.
They say that the strength of concrete is. Yeah. So if you're saying you're applying it, so apply it and give me a value, so that we move.
Okay, ma'am. I'm going to do it now.
I'm sorry, ma'am. Can you just please repeat your question?
The question is on the on the slide. You need to determine. So the thing is, I'm following with the gentleman because of the answer that he gave me. So he says we need to apply this formula: force over area. The formula force over area, meaning compressive strength equals force over area, to determine the force. So he says that the first thing we need to do is to determine the force, right? So because the question wants the approximate number of people the cube can support in compression. And we already know that our formula is that compressive strength equals force over area. So he says we need to determine first the force. So that's why I'm saying he needs to give me a value and tell me how he got to it, or if there's anyone who believes that
yes,
we can.
Yes, I finished that. I used the formula force over area to get the force, which would be 250,000 newtons, and then once I found the force, I used the formula force times mass times gravity, and then you have to first convert it to kilograms, and then you divide the answer by the 70. But it seems that I forgot to convert. Can I fix that problem now?
Okay, no problem. While he's fixing his problem, is there anyone who wants to say something regarding the question that's on the slide?
I got 364 people.
You got how many?
364 people.
364.
That's the same answer I got, but then there you have not converted. So hence I was saying that I need to fix my mistake.
What do you have to convert?
What do you call this? The force, because when you insert it to force is equal to mass times gravity, you won't insert it as 250,000 Newton. You'll insert it as a kilonewton. I don't know if.
But the strength of the concrete is in newtons per millimeter squared.
I'm not sure which is the right way, but yeah.
I don't think you convert. I think you only convert towards the end, especially since they said Newton meters. They didn't say kilonewton meters.
It's not necessary to convert from my side. Okay. I feel that if you do the calculation, even if you use newtons, and if you convert your 70 kgs to newtons, you can still get your answer of how many people. I'm also getting 364 people.
364.
Okay, I understand now. Thank you.
So can we agree and confirm that we are agreeing to an answer of 364 people?
Yes, ma'am.
You know, you can't say yes when you are the one who answered. There are people on the side as well who need to consider. They need to tell us, do they accept? Can we safely move and say everyone understands? Is there anyone who...
through it?
Ma'am, I think if people converted to the 70 kgs to newtons, they'd get an answer of 366.7. And if you convert your force to kgs and then divide by 70, you should get 364.
Mm-hmm.
So it's a matter of two difference between the two answers.
Okay. Is there someone who's lost before we even get to the 63, 66, 364, or whatever the case might be?
Yes, ma'am. Very lost, ma'am.
Where are you lost?
To getting to that 300 and whatnot, ma'am. Because from my understanding is you'll probably convert the kgs to newtons, and then obviously the area that you have is 10 cubic millimeters, and then from there, I guess what is it? It's gonna then be. I'm not sure from there, ma'am. Yeah, I'm lost from there.
Okay, let me ask you, sir. What is the force that you got? Because okay, we are going to say this. They said that calculate the approximate number of people 100 millimeter concrete cube can support in compression. So that compression part, it already takes us to our compressive strength equals force over area, right? So the first thing that we need to do then is to determine the force. Do you understand why we need to get the force first? Because if they say that assume the average mass of one person is 70 kilograms, according to Newton's laws, you know that force equals mass times the gravity mg. So meaning that we're moving, we're converting the mass into, or we need to determine the force. So the 70, you can easily say 70 times 9.81, and then you get your answer in newtons. So you already know that the average person, that's the amount of force they will exert on that particular cube. But you don't know to say if that is the amount one individual is exerting on the cube, then we need to know how much in terms of force can the cube hold first, because you already know that one person can exert this amount in newtons, because in kilograms it's already given. Then because the answer that you have there in terms of the compressive strength is already in newtons per millimeter squared, it only makes sense that you focus on this, because you can easily convert the area, or maybe the dimensions of the cube. The dimension of the cube that you're given is already in millimeters. When you look at the compressive strength answer, they say that it's 25 newtons per millimeters squared already. So you have that information. If you're, the only thing that is missing here is the force, and if you have the 100, it will be 100 times 100, because you already know if it's a cube, it's a square. Then it's 100 times 100 to get that force. Then to get the area. And then you multiply the area times the compressive strength. The answer that you're going to get there is going to be your answer in newtons. Then you already have converted the 70 kilograms to say how many, in terms of a force, how much is it, you already know. So you will get that value of newtons divided by what you already have in terms of newtons, and then it will give you the approximate number of people. So I'm just not sure in terms of, because you need to do it to confirm it in terms of the exact value, but it will be the approximate number. So that's why they say approximately, because it will have comma something, but because we're dealing with human beings, or we're saying number of people, then you just round it off and say approximately this number of people, assuming the one person or an individual is 70 kilograms. So is there anyone who's still confused in terms of, if you get a question like this, how you're supposed to move? Or the person that asked the question, do you understand now?
Ma'am, is it possible to write it down? Because I'm getting lost when you're explaining by word. I don't know about other students, but personally, ma'am, I'm getting lost when you're explaining about words.
I have the same
But I
issue.
understand why you convert
Yeah,
words
same, yeah.
to
Okay, so you have a cube, right? So they tell you that this is a cube that you have. This cube, they say it's 100 millimeter. You already know because it's a square, 100 times 100. Then it's the area. So we already know that the area of the cube is 100 times 100. It will give you an answer. So if you have 100 times 100, already you have an answer. They said to you that compressive strength, right? I'll just say compressive strength equals force over area. But they say they want approximate number of people this cube can hold, right? Or can support in compression. If the average mass of one person is 70 kilograms, when you look here, the compressive strength, this one, I'll just erase here and say already this value, they gave you to say it's 25 newtons per millimeter squared, right? Meaning force over area. This is squared. Force over area, newtons over millimeter squared. That's it. If you have here 10, 1, 2, 3, yeah, it's going to be 10,000. So if you have here that value, it means that you come here and substitute the 10,000. Where do you get it? You get it from there. That's the area. It means that we have a cube that they told us that the compressive strength is this. And they gave us a dimension. The only thing that's missing here, we don't know in terms of, if we say that in terms of force, that's what we don't know. They say that one person is 70 kg. If one person is 70 kg, the force there to determine will be that F equals mg, the mass is 70 times 9.81, and then you get a value. So here you'll get 686.7 newtons, right? Because here, that's what you have. So you have this value in terms of newtons. So this is a force that an individual person exerts on that particular cube, one person. But they said it's not only one person, the force is that amount. But we don't know in terms of force, how much can this cube hold? That's what we need to find out. That's where you'll say force equals 25 times 10,000, right? Because here, let's do it like that so that you understand fully. If here you have newtons over millimeters squared times 10,000 millimeters squared, this will cancel that, and the answer that you're going to get here, it's going to be in newtons. So here you'll have your 250, right? So the 250 that you get here, 250,000, it will be in newtons. So we already know that this is the force, the total amount in terms of force that the cube can hold. And this is the force one person can exert on that particular cube. If we want to know the number of people, it means that we're going to take this 250,000 divided by that 686.7, because that is the force for one person, assuming that one person is 70 kg, meaning that they will exert 686.7 newtons on that cube. Therefore, you will end up having the answer of 364.059. Right? So if you were the approximate number here, because the number after the comma is not over 5, then we can just say approximately 364 people will be accommodated by this particular cube. So do you now understand?
Yes,
Hello.
thank you, ma'am.
Oh, thank you. So basically that's it. One thing that I wanted to show you guys is how, when I was talking about application questions, how can they come? This is how you would normally get it if it was in a calculation format, because it's not theory based, right? So in a calculation format, still the principles of, or the basic thing is knowing that a compressive strength equals force over area. But how do you apply that knowledge in determining what is needed? Then this is how you would most probably need to navigate the questions or try to solve the questions. So because I've been getting questions of, can you share question papers, this and that, and I said, I can't share, but I can kind of give you an idea of, if you are seated and you're trying to study, or maybe read or whatever, try to make sure that you don't limit yourself. When you get a question, don't be quick to say, but you do not teach us that. This is something that is your knowledge, what we just learned in terms of compressive strength, and applying it or trying to think, will this make sense or not? Because the other thing that you may ask yourself is, but wait, how is this even possible? Because in principle, 364 people will never, ever stand on top of a 100mm cube, right? They will not be able to fit on that cube. But it is just to show you how strong that cube will be, as much as it will be small, because you saw that the cubes that we worked with in the prac, they were 150 by 150. And here they're not even talking about the 150 by 150, but 100 by 100. So it shows you that no matter how small it is, the strength of concrete is very big. And depending on the cement that you use, you will be able to accommodate very huge loads. That's why you are able to maybe have big construction things, like maybe your shopping complexes or malls or anything, and you're able to support cars, number of cars. So this is how it's possible, because look at how small that cube is, and look at the number of people, assuming that the compressive strength that we want is 25 newtons per millimeter squared. So it is just to show you that concrete is very strong, and that is how they're able to use it. And they're saying that is mostly used as a building material because of its strength and, again, the durability. So just note that other questions may come that will ask you based on that, on something that you already know. We discussed the durability of concrete. You know what is durability of concrete, you know what is a compressive strength of concrete, but the trick will be applying that knowledge and actually solving questions, or maybe trying to find a solution to something. That's all. So before we move forward, is there any other question? No question. If there is, please ask. If there's none, then let's move. Right. So the other thing that we're going to move to is the concrete deformation and volume change. Concrete deformation and volume change is something that happens. And how do we know this? We know this because we said during the hydration process, I will always go back to that and say, during the hydration process, what is the hydration process? Hydration process is the process whereby concrete hardens, right? It will move from the green state to a hardened state. When it's in the green or plastic state, we can still shape it into what we desire. But once it hardens, which is from 2 to 0 to 2 hours, then after that you can't change it anymore, right? So they say that concrete can deform and there is a volume change, right? So when we're talking about deformation, remember when you do the bending and the shear in when you determine in your structures, I think it's civil mechanics 1, where you deal with those things. So basically what they say is, normally think about it like this, because they already told you that concrete is good in compression but very bad in tension. If you have a beam, right, and you load it on top, what will happen is that it will sag, right? It means that it is not able to protect the load that you have, provided that the load that you have is bigger and it cannot be supported by that particular beam. It will tend to sag if it does not have reinforcement, or even if it has reinforcement but is not proper reinforcement in terms of the bars that you inserted there, they are not able to give you the desired strength. What it will do is it will deform, right? So they tell you that there are different ways concrete will deform. There is a deformation that you're going to get. So depending, if you have a beam, there's a different way it will deform. If you have a column, there's a way it will deform. If you have a slab, there's a way that you will get a deformation. But that deformation will happen provided that maybe you don't have, or the loading is too big, even if sometimes you have reinforcement, but the loading is too big, it means that you under-designed, right? So they tell you that concrete will deform and shrink. The shrinking part is the one whereby you already understand that because of the hydration process, it will tend to shrink, right? Because it's losing water. That's why we need to cure it over time to make sure that we allow it to gain the strength that it needs before it experiences any loading that may deform it or force it to shrink. So they say that the shrinkage is dependent on factors such as thickness of the concrete, humidity, and wetness of concrete. They also tell you that it is important to note this as you design structures, considering we have different types of loads: wind loads, imposed loads, and the dead load. So it's very important to note that as well moving forward, because you will need to know that the deformation will occur and the shrinkage will occur, and how will concrete behave when it has loads that are imposed on it. So they tell you that if concrete is loaded, it deforms immediately, then slowly continues to deform further with time. So there are two words that they use. You will hear the term elastic and creep. So elastic is used to describe the immediate deformation, and creep is used to describe long-term deformation. Let's just make an example. You see the cubes that we have, right, that you produced. Those cubes, we are going to crush them. So when we crush them, we put them in a machine, and on top there is a plate, a heavy plate, and it will crush the concrete. So what happens is it will tend to compress the concrete. So in that case, it means that before that concrete even fails in terms of cracks, because it will have mostly horizontal cracks, what will happen is we are not applying any tension on it. We are applying compressive strength, right? It will shrink. If we were to say this is a 150 millimeter cube, and we put it in that machine and we try to compress it because we're trying to load it, and we want to find out the compressive strength of that concrete before it fails, the highest. That is the compressive strength that we're going to get. If you're to measure the height, right, of that concrete, you will see that it deformed in terms, it will shrink by certain millimeters. So that's why they're telling you that as much as it will appear to be a solid particle, because in that format, it's solid, but still it does shrink. So that's what they're talking about. Under loading. So it's not like when you just place it there on its own, it will start shrinking. No, it will shrink because it will be under loading, right? And pressure. Let's just say that. So please note that as important information because you're going to use it moving forward. So if you are asked, then does concrete shrink? Then just because it's solid, it's a solid particle, don't say no. Be able to explain that if under compressive loading, then it is able to shrink, and these are the conditions and whatnot, right? Materials for concrete, we said that we already know that we have cement, water, and aggregates. So they say that cement is a substance that is used in a soft or plastic state, which then hardens to make things stick together. In this case, what do we mean by we wanted to stick certain particles together? We wanted to act as an adhesive or a glue per se to our aggregates, sand, and it will mix with water to create that, right? So that's what it is. So it is used as a binder, glue, or an adhesive. Common types of cements that they have is the ground granulated blast furnace slag, fly ash, and condensed silica fume. You can just read on your book how are they different, but those are just different types of cements that they can use. Cement extenders are used according to SENS standards. We already spoke about cement extenders. For instance, if you are working, okay, let's say you are if you are producing, let's say maybe you are building what's this? Let's say a bridge, right? Okay, you are constructing a bridge and you will need cement. And the cement that you need to use, let's say maybe it's a bridge that the water that will the bridge will be exposed to, it has maybe it's maybe ocean or seawater. We know that it has salt in it, right? It means that it's not like you'll use the same material or the same cement that you will normally use when you're building a house, because those conditions are totally different. So that's one thing that you need to note and remember, that the extenders may be used to slow or modify the concrete that you are trying to produce, right? Depending on what is it that you want to achieve. If you want to achieve maybe a rapid setting or a slow setting, you can use those extenders to achieve whatever it is that you may want to achieve, right? So you will modify cement modifiers or extenders. You can use them in those conditions. If you are maybe on a site and you want your concrete to harden as quick as possible, but not losing the strength or affecting the strength of concrete, then you will look into using those extenders, right? So there is also what we call the hydration of cement. Hydration of cement, they said that when you mix cement with water, the cement particles start to dissolve slowly and fibers grow from the cement particles into the water. On your book, they have a diagram that they did there to show you what do they mean by those fibers grow and into they grow from the cement particles into water. Let me just check on your books where you can find that diagram. The diagram is in page 104, right? So they show you that this is the hydration of cement. This is how it works. So they also tell you that during the hydration process, heat is given off. Therefore, in physics terms, it means that we're looking at an exothermic reaction because heat is given off. and therefore we have a reaction that takes place there, right? And we also said that in terms of curing, that's why we will cure concrete, because we don't want that when this exothermic reaction is happening, it will tend to harden, right? So if that process is quick, it means that our concrete will not gain the required strength quickly, the one that we need, or the specified strength. So we need to make sure that we control it. So there are ways. Remember, if I'm carrying a 150 by 150 millimeter cube of concrete in the lab, of course, it will be different from the way I will cure a slab, maybe 2 meter by 2 meter slab of concrete on site. It will be too different, because you can't lab and put it in water, all right? Because, I mean, it's too big. The slab on its own will be big. Okay, please. Can I please get a confirmation if you can still hear me?
Yes.
Okay, thank you very much. So basically what I was saying is there will be different ways to cure concrete, depending on where are you. If you are curing concrete on in the lab, it will be different because it's small and you can just put it in water. A slab, a 3 meter by 3 meter or 3 meter by 3.5 meters will be too big, maybe with a thickness of 200 or 150 or depending millimeters. It will be different from how you can cure concrete. You can make yourself a favor, just check the different ways you can cure concrete in the lab and outside, on site, because there are different ways. If you've seen a construction site, sometimes you see that they wrap these columns with plastic. That's a way of curing those the columns, but you can't wrap a slab with plastic. Then what do? Sometimes spray it with water, or spray with water and cover it with something if it happens that the slab that we're talking about is exposed to the sun or whatever. So just look at it in that way, that when you're producing concrete in small quantities, it may be easy to do certain things, but if you take the same concrete and you apply it on site and you have it in large quantities, then the way you would do things would totally differ. So that's the difference. And then the setting and hardening of concrete, they say that the dominant compounds in cement are calcium silicate, right? So basically the main ingredient that is the most important ingredient when it comes to the setting and hardening of concrete, here we're talking about cement. They say that cement, the main ingredient, the dominant compound, is calcium silicate. The calcium silicate will react with the water to produce a gel. So when this is the gel that provides concrete with its strength, right? So the calcium hydroxide, which is the lime, it will also be a product that we also get when cement mixes with water. It makes a gel or paste, and this paste is alkaline. And then they tell you that the high pH, because they say that this gel that will be produced when cement mixes with water, it is alkaline, and therefore what we have is a high pH. And then this high pH prevents the rusting of steel. Which steel are we talking about? The reinforcement steel. Therefore, that's why it is possible for us, even though we're using, because one person might ask, if we're saying that water makes a reinforcement to rust, because when we're discussing cracks, when we're talking about cement, we said that water will make the reinforcement rust if we experience any cracks. But then if you're asking yourself, if water is one of the ingredients that is used to make concrete, why then does it not make the reinforcement rust from the beginning? What happens is that cement that will react with the water. That's why you need to make sure that it is just the right amount of water. It's going to react with the cement and it changes to that gel, and that gel is alkaline, and therefore the steel will not rust. That's why they are specific, because they want you to understand that the gel is alkaline, and therefore that's why we can use uncoated reinforcement when we are producing concrete, or we are building or constructing these structures. So in terms of storage and handling, they just tell you that they have a long list of things and advantages and disadvantages. But the main thing is you need to understand that cement must be stored in such a way that it stays dry. So we don't want any moisture. We already know why, because any moisture that cement comes in contact with, it means that the cement will harden, and therefore we can not be able to use it because air contains moisture, right? So you need to make sure that it stays dry. And if you were to also look, if you were here in KZN, the air here is very moist because we're closer to the beach, and therefore it means that if you're storing concrete, it cannot be in an exposed environment, because you are in danger of having concrete that will harden. Or if you store it, you must use it. So mostly when you buy cement, you must not buy cement and put it there for longer periods. If you're using it, then you need to make sure that you use it as soon as possible, because you might experience that hardening of concrete, and therefore it means that the strength will be affected. They also tell you that contact with air should be kept to a minimum as well. So even if it's in areas, so if it's inland, same thing. It does not mean that you can expose it to air. It should be kept to a minimum as much as possible. So in terms of how they stack the cements and all the information, it's also in your book. And then for now, we will stop here today in terms of concrete and what it does. The only thing that is left, it will be the aggregates, the water, but the content in terms of the materials that are used in concrete is not that much. So it will be the aggregates and water. So they'll just discuss in terms of the water, how should it be? It shouldn't have any foreign materials in it, because, or any material that may affect the strength of concrete, and also the aggregates in terms of shape. Is it fine aggregates, or is the aggregates that we're talking about large aggregates? Then there is a difference, right? So those are the two things that we are left to do. And then the only thing I think we'll be discussing the joints, but I will just confirm with you guys if we will go into that, or it will be for information purposes, or maybe I will not assess it or not. I will share that information. But for now, I'll need to stop, because the main thing that we need to cover from now until 4 o'clock is the concrete mix design, because it's important, right? So I'm not saying the other things are not important, but this is something that we also need to make sure that we cover as soon as possible, because it's part of what you need information-wise to complete the preg. Not necessarily, but yeah, you also need it as well, right? So the second part that we will be doing is the concrete mix design. You already have the books, and in the book, so what I'm going to do is quickly, we're going to just move and look at what they have in the book. And from there, I'm going to give you a totally different example so that you understand. Maybe we have a different way of understanding, right? So if you go to your books and you turn to page 118, they talk about a concrete mix design, right? So a concrete mix design, when we were, from the beginning, when we were talking about concrete, we said that it can be specified according to the ratios or according to strength. How? We said that they can say, this is the ratio of all the ingredients and produce concrete, right? And this concrete that we need to produce should give us this, right? We already know because the proportions that we have will then produce a certain strength. Or what they can do is they just give you the strength and say, this is the strength. How you get to the concrete is up to you, or how you get to the different proportion in terms of the ingredients, it's up to you. So they can do that. You can either get a mixed design and you're told produce the concrete, or you are told this is the strength that I need. How you get to that, it's up to you. But just make sure that the concrete that you're going to produce will give me the strength. Then that's where the mixed design comes into effect, right? Because then what you need to do is you need to do your own mixed design calculation to find out in terms of proportions, how much of cement I'm going to use, how much of sand and aggregates do I need to use to produce that strength. So what they do is they tell you that is in a 5-step, it's a 5-step process. The first one is you need to select the water to cement ratio. This water to cement ratio, you're going to select depending on the strength that you need and the type of cement that that you have, right? So you have a ratio. In the lab, the ratio that we used initially, we said 0.5. Here, from table 2.6, which is in page 120, that is where you're going to get that ratio. How do you get it? Because you already know. They'll say, this is the strength of concrete that you need to produce. Whether you choose a different type of cement, then it will be up to you. In the examples, or because of because this is not an assignment, but maybe it will be in a test or that setting, then you will get maybe the same, not necessarily the same, but sometimes depending whether it's online or on site, then it might be different. But in per se, let's say, for example, they told you that the strength, right, that we need by the 28th day is 30 megapascals. So it means that they want the 30 MPAs standard. That's what they tell you. Let's say, for argument's sake, they tell you that the cement class that you need, or the cement that you need to use, is the cement strength 42.5. What you do is you go to table 2.6. You will note that the strength that you want is 30. The cement class will be given as 42.5, and therefore it means that the water to cement ratio that you're going to choose will be the 0.62. Number one. Just like that, you already have the water to cement ratio. Step 2, they tell you you need to estimate the water requirement based on water. For example, if I said that I will be using 26.5 stone, that's the nominal size. If you just go there, the water requirement for that is 200 liter per cubic meter. Per cubic meter. But there is a note just under table 2.7, right? Move with me, please. Table 2.7, it's a table where they tell you that these are the water requirements, right? So if this is the water requirement, provided the slump is 75, right? If you get a question, they say this is the cement, this is the strength, this is the stone size, you get here, but they say the slump is 100. It means that you will choose the 200, but you need to modify. Then it means that you will move to step 3. You need to modify the water requirement to suit the slump. I'll make an example. If you get a question and they tell you that the slump is 75, you're going to skip step 3. Why? Because there's nothing to modify. If they give you slump 100, you need to move to step 3 to modify the water requirement. How do they do it? If you have a 200, maybe let's say the one that we spoke about, because we said that the stone that we're going to use is 26.5, then you move there, you will either add or subtract the number of liters depending on the slump that you require. Remember, what makes the slump of concrete, we're talking about the consistency, the ability of concrete to move. Therefore, if you want concrete that is harder, it means that you will need to reduce maybe the amount of water. But if you want concrete that is going to flow, then it means that maybe if the slump that you have is maybe higher than 75, it means that that concrete needs to flow. It means that you need to add more water. So that's how you look at it. So you have table 2.6, you have table 2.7, you have figure 2.22. That's the figure we use to modify water based on step 3. Step 4 is the calculation of the cement content. How do you do it? You will have the water requirement in terms of liters. You already have the cement ratio that you would have had from table 2.6, and then you can determine the cement content in terms of kilograms. While you have the cement content in terms of kilograms, the last step, which is step 5, will be determining the stone and the sand content, right? So we're going to look at this. From the design process, we said we have 5 steps. The first one, water to cement ratio. Where do you get it? Table 2.6. Step 2, what do? You estimate the water. Estimate the water based on the stone that you're given. You do that. Step 3, you modify the water provided the slump is not 75. If the slump is 75 millimeters, then it means that you're going to use the slump as it was from 2.7, sorry, the water requirement as it was from table 2.7. The next step, what do? You calculate the cement content. How do you calculate the cement content? There is a formula. The water that you determined from table 2.7, and maybe you would have modified using figure 2.22. You take that water requirement, you divide by the cement ratio, that water to cement ratio that you got from table 2.6. From there, the last step will be determining the stone and sand of the mix, right? How do you do that? They will also tell you there is a formula, but that formula will have unknowns, meaning that you will have dry compacted bulk density. This is always given. The value of K, you're going to determine it using the stone size, the approximate slump that you have, and the type of compaction that they gave you. Go to table 2.8. Table 2.8, you see the approximate slump, 0 to 25. Heavy vibration. 25 to 100, moderate vibration. 75 to 150, hand compaction. So what does this mean? This slump shows you the type of compaction you're going to need to produce concrete that does not have any problems in terms of maybe you do not compact well. Other people during the practical, they do not get the 75. And some of you, please remember, when you looked at your slump, I even highlighted that the compaction was not well because we could see that the outside of the slump, right, was not smooth, in a sense that you could see that this is an aggregate. It means that this part also is an aggregate. When concrete is mixed thoroughly, it should provide concrete that does not have that. So the mixture should be in a sense that all the voids are filled with the finer particles. What does that mean? It means that because of some of you did not get that slump of 75, therefore a hand compaction would have not been appropriate in that manner. So if you were doing or producing a concrete that the slump is less than 75, for you to get proper compaction, you will either need to use moderate vibration or heavy vibration, right? So that's just one thing for you to note or remember. And on what do they mean by this, and why is it important that here you look at that, right? So sometimes it might not be that the concrete was hard. It might necessarily mean that the person who was responsible for compacting the concrete while it was in the slump cone was not exerting enough force. That might be possible as well. But we use table 2.8 to choose the value of K that we're going to use to determine the stone. The formula that you're going to use is the one there on step 5, ST equals CBD of the stone, which is the dry compacted bulk density of the stone, into K. K is the factor that depends on the nominal stone and the workability of concrete. And then what is FM? FM is the fineness modulus of sand. So what is given? You're going to get a question. They will give you the first thing, strength of concrete, the type of cement that you're going to use in our case. But if you're designing yourself, you need to find which one will be appropriate or cost effective, depending on the strength that you need. So in our case, we will get the strength. So you will get the strength of cement 28 days, the type of cement that you need to use, the nominal stone size, the slump, and the type of vibration that you're supposed to use. Those are the 5 things that you're going to need for you to determine or for you to do a mixed design. We'll go back. Selection of, so we are back to step 1, right? According to the example that they have in your book, they have 32.5 cement, right? 32.5 cement, and the strength that they have is 30. That's why in your book you see them circling that 0.56. They show you this is how you chose, because the strength that they requested was 32.5, and the MPAs at 28 days was 30. That's number 1. You move, you already have 0.56. Then you come to the depending on the stone. So they say that the stone that they're going to use is a 19. The water required is 210 for every cubic meter. This volume of water is based on a slump of 75. If the slump is under or above the value, above the 75, then you need to do step 3. So under step 3, they say that if the slump is the 75, then you leave it. If the slump is under or over, then you need to adjust. For example, the example that we're dealing with is the paragraph just under figure 2.22. They say, for example, the engineer specifies a slump of 100 in this example that we're moving with. Starting on the horizontal axis, you have a 75. And then because the required slump is 100, on the horizontal, we're moving from a slump of 75 because we're moving from the 210 that was given. But the 210 is based on the understanding that the slump is 75. But we already know that our engineer said, no, I don't need a slump of 75, but I need a slump of 100. Therefore, that's why they're saying you need to move from a slump of 75 to a slump of 100, right? To a slump of 100. So you will draw a vertical line from the 75 and a horizontal line to 100. Where those points meet, that is where you are. So in this case, look, they say assume, therefore, that an extra 5 liters. How did they do it? On the, okay, let me do this so that we have an understanding. Senzela, please switch off your video. Thank you. So this is where I am, right? I need to explain to you table figure 2.22, the adjustment of water. How do you adjust water? Figure 2.22, what do they have? So figure 2.22, this is what they have, right? It might not be as, okay, let me just do this. Oh no, not this one. Let's choose this one. Okay, rather let's choose this shape. So say no. So this is what they have, right? So this is what they have. They have from here. Okay. So this is what they have. From here, they have from to, right? So we're moving to the slump of from that slump. Why? From a slump of 75, because that's where we were moving from. Initially, we were told our slump is from 75 according to the table, right? So they have here 25, 50, 75, 100, 125, 150, and so on. This side, they have the same 25 from here, 50, 75, 100, 125, 150, and so on. And then they have lines, right? The first thing that you need to do, what you don't have on your book, they have different lines from, if this is 150, they have lines, diagonal lines like that are moving in that direction, right? So these are the lines that they have. I'm trying to imitate what you have on your this is what you have. So I need to show you how do you then adjust, right? So before we go there, they have here you minus 6 liters, 6 liters minus 12, minus 18, and then minus 24. This side you also have the same. You add 6, add 12, add 18, and then finally here you add 24 liters of water. So that's what you'll add depending on where your point is, right? So the first thing that I said you need to do is you need to take a ruler, extend a line. So you place your ruler in this way that we're trying to find a common, we're looking for our 0 line, right? So this way. Let me just do one. It will not be straight. Yours is supposed to be straight, but because you're using a ruler. That's your line, straight line. This is your 0 line, right? Anything below this, you minus. So if you're here, right, because there will be a scale, you will see on your, you will have here, you will have lines that you will create yourself, because there is, when you look at the distance from there to there, you will adjust depending on what do you have. So you can either have lines that are going in that direction, but if let's say you are at this point, what is happening here is 0. If maybe it's from 75, if you construct a line, right? Let's just make an example. If right now you construct a line from 75 to 75 in your graph, the one that you have in your book, it will land on the 0 line. It means that you don't need to do anything. You don't need to adjust anything there. If you move from 100 to 100, all of them will fall onto that. It means that there's no adjustment, meaning that there's 0 adjustment, right? If you move from a 75 to 100, in this case, right, our 100 will fall somewhere, let's say somewhere here. But we are not there. Let's come back to this because we already have these lines. This is a 0. If you were to fall on this point here, what were you going to minus? 1 liter. You fall here, what do you minus? 2 liters. Here, 3 liters. There, 4 liters. There, 5. If you get to this point, because it's on the line, that's where you minus 6 liters. Same. If you go up, this is 1, 2, maybe 3, 4, 5, and that's 6. If you fall at this point, what do you add? 1 liter. Here, what do you add? 2, 3, 4, 5, and finally, if you fall on the point there on the line, it will be the 6 liters. So what's happening in terms of your the slump that you have? They said from a 75 to a 100. 75. Let's remove these ones because we'll have a problem. So this was our line, our 6 liter line. So they said from 75 to 100. What do you do? Construct a line from 75 up to where? To 100. What do you do? A line in that direction. Where these points intersect, that's your adjustment. We said here you have a 0 line. You add 1, 2, 3, 4, 5. That's why on your book, they said they had an adjustment of 5 liters. Because of the scale, you see, the 5 liters will fall there. It will be just a point above the, if you move a point towards the line, you will be at 6 liters, right? So that's why they're saying add 5 liters. If they were to say move from 100 to maybe 125, right? If this was 125, somewhere there. But remember, mine is not on scale, but on your book, you'll see. For argument's sake, let's use mine, the one that is not on scale, and say they said move from the slump of 75 to maybe 150. Where's your point? Your point will fall here. What do? You will have those grid lines going that direction. 1, because this is 6, then you'll have 7, 8, 9, 10, 11, and then finally that is 12. So according to scale, maybe if this was the thing, then we will be required to add 10 liters to what we already have. If initially we had 200 liters, we will add plus 10 because that's the adjustment that we had. In our case, they said the adjustment was 5 liters because the slump was from a 75 to 100. Do we all understand this part of the adjustment of water? You only adjust if the slump is below or over 75. If it's specified as 75, you will use 75. We all understand, right? Yes. And then they moved to 215. Remember, the 215 will be the water requirement because it was 200 plus 5. So you no longer have 200 liters. No, you no longer have 210, sorry, but you have 210 plus 5. That's why they have 215 divided by the water to cement ratio. And then the other ones, you apply the formulas to get the values that you need to determine. So what I'm going to do is let's rather look for an example that we're going to start from beginning to end, and then we do it together so that you follow, right? So the idea is have your books with you and make sure that you follow. You need to make sure that you follow. It's very important that you do follow. So I'll just look for the formula. While I'm looking for this, is there anyone who says they don't understand? Yes, no? Okay, no problem. Then let me just find the example that we're going to use, and then we follow each other and complete that.
Sorry, ma'am.
Yes, sir.
Can you say that the lower your slump is, generally the stronger your concrete will be?
Not necessarily, because that depends. Remember, the strength of concrete is not dependent only on the slump, but it's dependent on the stone that you're using and also the type of cement, right? So the issue of slump is mostly related to the workability of concrete. So if you have a concrete that is hard, it means that with a lower slump, it means that it's not workable. Therefore, you will need high, heavy vibratory or poker vibration to make sure that you're able to vibrate it. But it's not dependent on, it does not necessarily guarantee that concrete with lower slump will generally be strong. The strength of concrete is dependent on other factors, such as the stone that you're using. Because remember, the density of the stone. So if, let's say, for example, you have a 9.5 and you have a 26, the other one is smaller, the other one is way bigger, therefore the strength will differ depending on those, and also the type of cement, because the bonding is based on that as well. So the slump on its own does not necessarily tell you the strength of concrete, but is mostly relating to the workability.
Okay, thank you, ma'am.
Okay, thank you, sir. Give me two minutes. Let's just try to do this. Wait. Here we are. So what they have here is they say that the figure shows a cross section of a concrete curb that is 1 meter long, right? You are requested to determine the quantities that will produce 100 curbs. So that's number one. And then those are the dimensions of the curb. And this is the information. So they tell you that the relative density of cement, 3.14, relative density of stone, 2.71, relative density of sand, 2.8, stone size, 19, fineness modulus of sand, 2.9. Dry compacted density of stone, 1,960 kilograms per meters cube. The concrete strength required at 28 days is 35. The concrete class is 70% cement with 42.5 strength and 30% fly ash. That's the cement that they want you to use. The slump is from 75 to a 90, and the concrete is to be hand compacted. So we're going to move together. We're going to move together, and you're going to look at the information that you have. What do they want? They want quantities that will produce 100 cabs in terms of what? Volume. So you need to find out the first thing first. The amount of volume that is 1 cab of concrete, how much in terms of volume, and you multiply that by 100. So you will have the total volume that you're going to need. You put that aside, it's something else. And then you go back, you say, these are the requirements, right? So what they want is the quantities. You are requested to determine the quantities. Which quantities? The quantities what we need is how much cement, how much in terms of even weight, how the cement that you're going to need, the amount of water, the aggregates, and the sand, the amount of sand that you're going to need to produce whatever it is that you need to produce. So that's what they need, meaning that you need to give them that information, right? So the first thing, what did they say? Step 1, water to cement ratio. If you look at the information that is given, can you indicate the cement ratio that you need to the cement ratio that you are going to use? Provided, remember, concrete strength required 28 days, 35 MPAs, the class 70. The water to cement ratio, please just say it out loud so that we move to the next one.
0.47.
0.47. Okay, the amount of water initially that we needed?
210.
210. Okay. Do we need to make any adjustments?
Yes.
Why?
Because the slump is moving from 75 to 90 millimeters.
Okay. Look at your table and try to give an approximate number. How many liters do you think we will need to either add or subtract? Do we need to add or subtract? And if so, the amount of water?
We would need to add approximately 4 liters of water.
4 liters.
Yes, ma'am.
Does anyone agree to the 4 liters?
Yes.
Anyone who has a different, anyone who does not understand how we got the 4 liters? Okay. Okay, we go back. We already have the water to cement ratio as 0.47. We said that our initial water was, because of the nominal stone size, it was 210, and then we adjusted it. We said 4 liters. Therefore, it means we have what? 214 as water. Can you then determine the cement content? The cement content?
455 kilograms.
Do we agree with the value?
Yes.
Anyone who does not understand? Then we move to step 5. Step 5, can you give me the value of K? K value? K value?
0.94, ma'am.
0.94. Can you determine the stone content required? Using the formula?
Sorry, ma'am, I don't understand how you're finding the K value.
How the K value? Okay. Go to your book, page 122. Are you there?
Yes, ma'am.
Okay. Look at the question that's on the. Look at the question that is on the shared screen. They said the stone size that you're using is what? The stone size. Please tell me.
19 millimeters.
19 millimeters. What did they say about the slump?
It's moving from 75 to 90.
And the type of compaction?
Sand compaction. Okay, I see, ma'am.
Okay. Thank you very much, sir. So please tell me the value that you get as your stone content.
1,274.
Do you all agree with the value?
Yes.
Okay, let's move forward. Remember, we are done with the stone content. We need to determine the sand content. When you're determining the sand content, the first thing that you need to do, you need to determine the volume of sand. How do you determine the volume of sand? You do that using the formula on page 123. The one that says volume of sand equals mass of sand over relative density of sand. Down there they break it down, right? It's either you were going, if you were given in terms of volume, you can also say 1 minus volume of cement, the sum of volume of cement, stone, and water, but we don't have that information. But rather, what we have is this information, right? You have the mass of cement in kgs that can produce a 1 cubic meter of concrete. You have it. You have the stone content. We just determined that. You have the relative density of sand. It's given. You have the relative density of cement is also given. You have the relative density of stone is also given. Therefore, you can apply this information on the formula, because even the volume of water in terms of liters you do have. So you apply, you just substitute those values in the formula to get the volume of sand. As soon as you get it, you will multiply that value with the relative density of sand. In their case, it was 2.72. In your case, what do you have there? It's there on your on the table. Relative density of sand is also given. So please apply the information that you have on the formula and give the value of the volume of sand. Volume of sand, anyone? Anyone? Unmute yourself if you want to say something. Because I'm in a presentation mode, I can't see if you raise your hands. Just ask if you want to, please. In the meantime, I'm still waiting for someone to tell me the volume of sand. volume of sand. Volume of sand. Hello.
Yes, ma'am, we're still trying to work it out on the side. Ma'am?
Yes.
Myself ask, when you're trying to solve the volume of the curb, which length are we going to use? Because I'm oh, 1 meter long. Oh, okay, ma'am, thank you.
But how did you get to the 1 meter long when you have not given me the volume of sand? Can you please, guys?
You were showing me the answer because I was asking as the length of the curves because there's two dimensions here, and unless if I'm mistaken.
What do you mean?
Like volume is height times base times length, right? So then here, because the way I'm solving it, I divided the shape into smaller shapes, and
no. Wait, I'm not requesting the volume of the curb. We need to determine the quantity before we even get to where you are right now. We need to find the exact values for cement, stone, sand, water first. And then we can move to the part where you need to, how do you apply that information to the volume of the volume that you are determining right now. So right now, we are not even looking at the curb at all.
Okay. I'm lost. I would be lying now. Because
wait. Go to page 123. What I said is you have two formulas to determine the volume of sand, right? You can either use the first one or the second one. In terms of information that is given, we are able to get the volume of sand using the second formula. You see up there, it says volume of sand,
yes,
and then it says or also volume of sand. Use the formula, use the second formula, the one that says 100 minus C, 100 minus, and then you open brackets C over RDC plus ST over RD stone plus the volume of water, close bracket. That is the formula you're using.
Oh, okay, ma'am. Thank you. I'm gonna try now.
By the way, we're not dealing with one person. Can we please, because the other people already used the right formula, can we please find the value so that we move?
170.98.
So do we all get 170.98? We agree with the answer? If no one is saying anything, I'm thinking that we agree. So take that 190.78 that you got, you multiply it with 2.72. sorry, no, not 2.72, the relative density of sand. Relative density of sand, and the value that you get there is the sand content in kilograms per meters cubed, right? So please give me, I need you to give me the values that you got, right? So in terms of cement, how much do you have? Cement?
The cement was 455 kilograms.
Stone? Stone?
1274.
Sand? I'm looking for sand.
$478.47.
478.
Yes.
I need you to note something, right? As I was writing these down, even in your book, they do indicate per cubic meter, meaning that if you were told determine the quantities, right, that will produce a 1 cubic meter of concrete, these values you would stop here, right? And what would you do is you will just then adjust them in terms of water, sand, sorry, cement. You'll start with the cement, sand, and then stone, right? So that is what you would have. And then remember, initially in the lab, we had 1:2:2. We said this is the cement, sand, and then stone, right? So that is what we had. You will also do the same. You will take the cement, stone, sand, right? This is what you would have, and then write it in terms of a ratio. That is all. Those will be the quantities required to produce 1 cubic meter of concrete. In our case, we are not producing 1 cubic meter of concrete. Rather, we have concrete here that is given that we need to produce. So you have this in terms of, because the cab is small, right? The cabs are small, and this is in terms of the values that you get here in terms of, millimeters. Then you need to determine this, convert that into meters squared, multiply that by the length, right? So it will give you 1 cab, meaning that 1 cab is that amount of volume times 100 for you to get the total volume. So you need to do that. You can just cut it into different sections and then determine the volume. That's one thing that you need to do. Once you get the volume, remember, sorry, to get the area. Once you get the area, you multiply that by the whole length to get the volume. Once you get the volume, you times that by the 100, because you need 100 cabs, but not 1. So once you're done with that, remember, let's say, for argument's sake, it gives you 100 meters cubed of concrete, right? 100 meters cubed. It means that this is the volume. What then you need to do is you need to find out in terms of kilograms, because you already have the volume, you'll multiply this by 100 if it's 100 meters cubed. So I'm saying I've already determined my volume hypothetically, and the total volume that I get is 100 meters cubed. Then I apply that here. Why? Because the values that you got here is kilograms per meters cubed. So you will need 455 kilograms of cement to produce 1 cubic meter. 1 cubic meter of a volume. But if you have 100 cubic meters, then you will times that by 100. If the value that you get there as your total volume is 20 cubic meters, meaning this is your volume of concrete that you need to produce. But here, the cement that you're going to need, you just multiply that by this value, because you're going to need that 20 cubic meters, but not 1, 20 of them. So basically, that's it. So that's how you will solve this question in terms of if they specified the amount of concrete they want you to produce, then you will tell them the quantities. If they just say determine the mixed design, then you will just stop here. You will not multiply these values by anything, but what you will do is you will just say convert them into a ratio, and then you will have that ratio. That's all. So do we all understand? Essentially, that is a mixed design. Is there anyone who's lost? So the issue of determining the volume, because it's just the area that you need to determine times the length to get the volume, times the amount or the number of cabs you need to produce. You can do that on your own. It's not a difficult thing. So you already know how to navigate the tables to get to this point, which is the most important part of the mixed design. Because here, if you were told do a mixed design, you will stop here. But this did not say do a mixed design. It says you are requested to determine quantities that will produce 100 cabs. So are we all together? So I can safely say you all understand the concept of mixed design. Yes, no?
Yes, ma'am.
Yes. Is there anyone who says, I don't understand, I was lost, or you lost me somewhere? None. Okay. If that's where we are, then thank you very much. It means that we have successfully completed the mixed design. No, you now understand what is different from what you got during the preg. During the preg, what did we do? This process of the mixed design, it was already completed. You were given the ratios, and you just needed to mix and produce the concrete. Whether the concrete will yield the required strength or not, I'm coming, Sibego. Whether the concrete will produce the required strength or not, that will be dependent on how we did. Were there any errors? Was there a problem with the cement that we used, the water that we used or not? Then those factors, or the curing of concrete, and then that will affect the strength of concrete. Yes, Sibego?
I just wanted to know, ma'am, is it possible maybe to get like some more examples that you have so that we can practice?
I don't have them. So basically, I think what you can do is you already know a mixed design. You know what is required. You have your example on the book. I provided an extra example. You can play around with them and change the volumes if you want to, or give yourself a different structure and then see how it is different. But the only thing that is tricky about the question is making sure that you understand and adjusting the water accurately. That's all, because the other things you just choose and then you move. So in terms of because on your book, they showed you this is how you do a mixed design only, right? Without anything. The example that I gave you, it's not only a mixed design, but it's an example about you determining the quantities. If you want to move forward and practice, how do you do quantities? You can give yourself, you can maybe say you have a slab of 15 by maybe 15 meters by 5 meters by 100 meters in thickness, and then you produce that concrete, and then you do the quantities. But in terms of any examples, I won't be giving any examples, because I think I've covered how do you do the mixed design itself, and how do you go about if you were to determine the quantities. Then anything moving forward, it's your practice that you can do on your side. I think you can try to find them on Google. I'm sure they will have, or you can play around with different things, like if it's a slab or column or anything that is concrete based, or maybe a concrete pavement, then you just change dimensions and then you produce it. But that's all. In terms of what is tricky about a mixed design is understanding and capturing the information well from the beginning, and making sure that you do the adjustments correctly, and then everything else is just the multiplication. Or maybe if you're given a structure, you are able to determine the volume accurately. But that's all. I don't think it's difficult or tricky in any way. So from my side, this is where I'll stop in terms of additional information and examples. If you have an additional question, or there's something, you have a question that you don't understand, you can put it, and then we can to solve it. I don't have a problem. But on my side, I won't be sharing any more examples. Is there any other question? No question.